Hello everyone. So today we are going to talk about permutation with indistinguishable objects on page 10. So let's start with example 19a. How many different strings can be made by reordering the letters of the string ABC? So you have a string with 3 letters ABC. How many different strings can you make by reordering these 3 letters? Let's see. So you have 3 different letters and you want to permute them. So from the formula we know that the answer is 3 factorial. 3 different letters. If you want to permute all of them, there are 3 factorial different ways of doing that, and you generate different strings. Just for some example, let's see what are these 3 factorial or 6 different strings: A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, and C, B, A. 1, 2, 3, 4, 5, 6 different strings. This is just for example, we don't need to show that. This is your answer. So part A answer is 3 factorial. Now let's do for part B. We have the string 5 letters A, B, C, and we're asking the question, how many different strings can we make by reordering all of these letters? So these 3 A's, they are all same, that's why they are indistinguishable, but they're different from B and C, so we have to be careful with that. For example, let's do it this way. We make them distinguishable. Okay. How do we do that? So we have the letters A, B, C. They all look the same, so let's first make them different. A1, A2, A3. Now that we numbered them differently or labeled them, they are all different. So now they are distinguishable. So now we have 5 distinguishable letters. Okay. How many permutations? Easy. 5 factorial. We have 5 distinguishable letters, so 5 factorial. Now we have made them forcefully distinguishable. They are actually not. So how many of them are actually the same string? Let's see. So you can have like this string or this string, okay. This string is actually same as this string. Also same as this one. For example, this one, this is also same as this one, same as this one. These are same. These are also same actually, because A1, A2, A3 is same as A1, A3, A2, since they are all actually A's. So how many of these are here that are same? So if you see A1, A2, A3 and all their different permutations, they are actually same. So there are actually 3 factorial of these that are same. Similarly here A2, A1, A3. And if you just focus on the A's, all different 3 factorial permutations, they are all same. What does that mean? That means this result 5 factorial is overcounting, and we overcounted each string by 3 factorial. So 5 factorial over 3 factorial is the correct answer, which is 5 times 4 equal to 20. Okay, so that's your correct answer. So what is the formula? You look at how many letters are there. There are total 5 letters. Okay, so 5 letters, 5 factorial over how many of them are same? 3 A's are same, so 3 factorial. 5 factorial over 3 factorial, 20 is your answer. Now do the last part, C. How many strings can we make by reordering these letters? 3 A's, 1 B, 2 C's. Okay, we learned the new formula, so we are going to use it. So total 6 letters, 3 A's, we can put that 1 B and 2 C's. Okay, so the answer is 6 letters, so that is 6 factorial, that goes in the numerator, and the denominator you have 3 A's, so 3 factorial, 1 B, so 1 factorial, 2 C's, 2 factorial. So that is your answer. If we simplify it, it's 6 times 5 times 4 times 3 times 2 times 1. And here we have 3 times 2 times 1 times 1 times 2 times 1. Okay, so 3, 2, 6, and 2 goes from here, so we are left with 5 times 4 times 3, which is 60. Okay, so just to repeat, the formula is, in the numerator it goes how many letters are there in total, factorial of that. Then in the denominator, for each type you find how many are there, repetition, and factorial for each of them. If there is 1, you can put it, you can ignore it, since 1 factorial is just 1. Next, so we sort of formalize this theorem, theorem 4 on page 10. The number of different permutations of n objects, where there are n1 indistinguishable objects of type 1, n2 indistinguishable objects of type 2, up to nk indistinguishable objects of type k. That number of different permutations is, in the numerator it's n factorial, the denominator is n1 factorial, n2 factorial, up to nk factorial. Our next topic is distributing distinguishable objects into distinguishable boxes. That means the objects are all different, distinct, and the boxes are also distinct. The number of ways to distribute n distinguishable objects into k distinguishable boxes so that ni objects are placed into box I equals. So let's see. This is how it looks like visually. So you have k boxes, they are all different. Box 1, box 2, box 3, up to box k. And you have n objects here, they are also all different. And we are trying to put n1 objects here, n2 objects here, n3 objects here, nk objects here, and asking the question how many different ways we can do that. Let's see. So if we choose n1 objects from here and put it over here, how many ways to do that? N choose n1. So from n objects we choose n1 of them and we put it in the first box. Okay, so this is filled. Next, this one. So how many objects are left now? Now there are n minus n1 objects left. So from that n minus n1 objects we are choosing n2 and we put it in the second box. Okay, then we still multiplying. Now how many objects are left? N minus n1 minus n2, and from that we are choosing n3 objects and put it in box 3. So n minus n1 minus n2, we are choosing n3 objects, and that goes on. At the very end, so this process, you fill up all these boxes, and at last you are filling nk objects here. For that, how many objects are left? n1 minus n2 minus n3 minus nk minus 1, and you choose nk of them and you fill up the box. So this is this product, entire product is the formula, but you can actually simplify it. So let's simplify the first factor. N choose n1. What is the formula? We all know n factorial over n times n minus 1 factorial times n1 factorial. Then if we solve this one, this is n minus n1 factorial over n minus n1 minus n2 factorial times n2 factorial. We are not going to do this. Let's just do the last one. Last one will be n minus n1 minus dot 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 up to this last one factorial over n minus up to nk factorial times nk factorial. And you'll see that all these, they cross off. This one will cross off with something here, and this will continue. This will all be gone. What you are left with is a familiar formula: n factorial over n1 factorial, n2 factorial, n3 factorial dot 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 nk factorial. Okay, so final answer is actually much simpler. n factorial over n1 factorial, n2 factorial, n3 factorial up to nk factorial. The same result as theorem 4. Now let's solve example 20. How many ways are there to distribute hands of 5 cards to each of the 4 players from the standard deck of 52 cards? We are going to use the technique or the formula we just learned. So for the first player, we have total 52 cards and we choose 5 for that person, times then the second player, how many cards are left? 52 minus 5, and we choose 5 for that person. Third player, how many cards are left? 52 minus 10, and we choose 5 for that person. And for the fourth player, how many cards are left? 52 minus 15, and we choose 5 for that person. Okay, so that is the final answer. If you want to simplify it, this is 52 factorial over 52 minus 5 factorial, 5 factorial. 52 minus 5 factorial over 52 minus 10 factorial, 5 factorial. 52 minus 10 factorial, 52 minus 15 factorial, 5 factorial. 52 minus 15 factorial, 52 minus 20 factorial, 5. This cancels this, this cancels this, this cancels this. The final answer is 5 factorial, 5 factorial, 5 factorial, and 32 factorial. So this is 32 factorial. So that's your final answer. 52 factorial over 5 factorial, 5 factorial, 5 factorial, 5 factorial, 32 factorial.